So what does our mass spectrum look like? Well, here you see that we have relative abundance on the y-axis and mass to charge ratio on the x-axis. So remember that our charge in this case is going to be +1. So on the x-axis we essentially have mass. And then we have relative abundance, so that indicates the abundance of that particular ion that's hitting the detector. And we're going to see that's a key to understanding a little bit about the structure of our molecule. So we also see something called the base peak. The base peak is the tallest peak in the spectrum. So the tallest peak is going to give a relative height of 100%. And we're going to see that that'll be important in calculating our molecular formula. So this is the mass spectrum for methane. Methane has 1 carbon and 4 hydrogens. Carbon has 6 protons and 6 neutrons. And hydrogen, in this case, this is the most common isotope of hydrogen. This is just regular hydrogen, has just a proton in the nucleus. So remember that the atomic mass unit, or the units of atomic mass units, are based on carbon-12 having 12 AMUs, and all of the other isotopes of the different elements are based off of that. Well, the spectrum that we have here is rounded to whole numbers, and so we just say that 1 proton is 1 AMU, 1 neutron is 1 AMU, and so just using whole numbers for those, we can say that carbon-12 weighs 12 AMUs, and each of these hydrogens is 1 AMU each. So that means that this molecule of methane weighs 12, 13, 14, 15, 16 AMUs. Okay, and so we can see that here on this spectrum. So in fact, our molecular ion peak is the tallest peak in our spectrum in this case, which is our base peak. Okay, so this would be our M+ peak, or our molecular ion peak. And in this case, it's our base peak. It's the tallest peak of the spectrum. It represents 100%. So that our tallest peak is given a value of 100%. And then we have another peak that's a little bit smaller at 15 AMUs, and that is going to represent this molecule that fragmented and lost a hydrogen somewhere along the way. Then if it lost 2 hydrogens, then we're going to see we have 1 less here at 14. Losing 3 hydrogens would give us 13, and then losing 4 hydrogens is going to give us 12, which would just be a carbon atom. So this is the general structure of different peaks in the alkane, different fragmentation of alkanes. We're going to see we have bigger, smaller, smaller, smaller for each, say, methyl or methylene group. So we'll look at that a little bit later on. But basically we have mass to charge ratio, where mass is given in AMUs, versus relative abundance in the spectrum. Okay, so here we have a molecular ion peak for methane, and that would be at 16, and we see that it lost a hydrogen. If it loses a hydrogen, it can fragment and give us just CH3, which would have a mass to charge of 15, and we saw that in the spectrum. And so different fragments can give different peaks according to their respective mass to charge ratio. Now here we have a mass spectrum for benzene. Where do you think our molecular ion peak would be for benzene? Okay, so benzene actually weighs 78 AMUs, because we have 6 hydrogens and 6 carbons in this molecule. And so since it weighs 78 AMUs, we can see that right here on the spectrum. And in fact, the molecular ion peak, or the M+ peak for benzene, is in fact our base peak. It is the base peak, and it represents 100%, because our relative abundance for our tallest peak is given a value of 100. So you can see that benzene doesn't fragment easily. Remember, benzene is an aromatic compound. It's aromatic, and that aromaticity makes it particularly stable. So the molecular ion peak doesn't fragment as much as some regular alkanes would. Okay, here we have pentane, so we have the molecule represented here, and you can see that pentane fragments easily. In fact, the base peak isn't nearly the molecular ion peak. So the molecular ion peak for pentane would be what? So we have C5 H what? 12. And so let's see, I had some notes around here somewhere. I'm looking for my notes. I don't see them. Anyway, so this would be C5H12. So the carbon weighs 12, so 5 times 12 is 60, plus 12 hydrogens is 72. So we could expect our molecular ion peak to show up at 72. So our M plus peak is going to be at 72. Okay, so our base peak is located here in the spectrum, and we're going to give that a relative height of 100%, and it's located at 41, 42, 43. Okay, so our base peak is located at 43. And so we can see that this molecule fragments very, very easily in GCMS. So the first step in analyzing a mass spectrum is to try to identify the molecular ion peak. And that's not always easy, because if the molecular ion peak is the result of a highly fragmented molecule, it may not even be in the spectrum. And it will tell you exactly the molar mass of that compound. So if the molecular ion peak is odd, then it can indicate an odd number of nitrogen atoms in the molecule, which, remember, can so remember that if it's odd, then we can have an odd number of nitrogen atoms, which results from the bonding pattern for nitrogen having a different number of hydrogens on it than relative to a saturated hydrocarbon. So if it's even, then it could either be just a regular hydrocarbon, or just another type of molecule, or something even with an even number of nitrogen atoms in it. So if it has an even number of nitrogens or no nitrogens, then it's going to have an even molecular weight. If it has an odd molecular weight, then we can have an odd number of nitrogen atoms in the molecule. Okay, so let's look at what the M plus 1 peak means. So notice this little bitty peak over here. Okay, so that's higher than the weight of this methane. So remember, methane is 16 AMUs, but this thing is showing up at 17. So why would we have a peak at 17? Well, that's called the M plus 1 peak. That means our molecular ion peak plus 1. And that results from a little bit of carbon-13 in the sample. So the different isotopes of the different molecules don't hit the detector at the same point. They're actually separated. The different isotopes of atoms are separated in a mass spectrum, because these isotopes are going to have different weights. So carbon-13 actually has a different weight, and it's going to hit the detector at a different point, but we don't have as much carbon-13 in nature. It's not as abundant in nature as carbon-12. And so we get this little bitty peak, which represents some of the methane molecules having a carbon-13 in them. And this results in a peak at 1 higher, because we have carbon-13 versus carbon-12, 1 higher AMUs. And notice that's very small. So methane, the M plus 1 peak is going to be about 1% as abundant as the molecular ion peak. So it turns out that for every carbon atom in the molecule, we're going to have an M plus 1 peak that's equal to 1.1 times the number of carbon atoms in the sample, because carbon-13 makes up 1.1% of all carbon atoms in nature. And this is a key to finding our molecular formula. So for every 100 molecules of something like, say, decane, we have an M plus 1 peak that's going to result in a relative abundance that's 11% as high as the molecular ion peak. okay, because it's 1.1% as high for each carbon atom, and for decane we have 10 carbon atoms, so it's going to be 11% as high as the molecular ion peak. Okay, so let's think about how we could use mass spectrometry to distinguish between some compounds. And this is the kind of thing that you would see on the 231 final, on the Organic Chemistry 1 final exam, potentially, is how would you use mass spectrometry to distinguish between different compounds. Okay, so let's look at A. So here we have furan, or we have furan, and so this molecule, notice these carbons are sp2 hybridized, so each one of those carbons is going to have a hydrogen on them, and we have an oxygen. So what is the molecular formula for this molecule? We have 1, 2, 3, 4 carbons, so that's C4, and then we have 4 hydrogens, so that's H4O. Okay, so that's going to be 12 times 4 plus 4 plus 16. So the atomic mass for oxygen is 16. Atomic mass for hydrogen is 1. We got 4 of them. So we've got 4 carbons. Each one of those weighs 12. And so that's going to be a molecular weight of 68 for this molecule. So we can expect our molecular ion peak to be found at 68. So what about cyclopentadiene here? So cyclopentadiene has 2 hydrogens on this carbon, because this one's sp3 hybridized, and 1 hydrogen on each of those other carbons. So its molecular formula is C what? 5, 1, 2, 3, 4, 5, H what? 1, 2, 3, 4, 5, 6. Okay, so that's going to give us 12 times 5 plus 6. Okay, so that's going to be 60 plus 6, which is 66. Okay, so we could expect our molecular ion peak to show up at 66 for cyclopentadiene. So we could easily distinguish between these two molecules in mass spectrometry. Excuse me. So what about these two molecules here? So let's look at B. Okay, let's look at B. So here we have benzene. Benzene has 6 carbon atoms and 6 hydrogen atoms, so that's 12 times 6. So 12 is the atomic mass of carbon times 6 carbons plus 6. That's 6 times 1 for each hydrogen, is going to be equal to 72 plus 6 is equal to 78. So the molecular weight of benzene is 78, and we saw that spectrum earlier. So our molecular ion peak for benzene is going to be found at 78. Okay, so what about pyridine here? So we have this molecule has 1, 2, 3, 4, 5 carbons, so it has shoot, I don't think I can control that. No. So that's 12 times 5, okay, plus 5 hydrogens, okay, plus the atomic weight for nitrogen, which is 14, and that's going to be equal to 60 plus 5 plus 14, which is equal to 79. So the molecular weight for this molecule is going to be 79 versus 78. So we could also distinguish between these two molecules in GCM in mass spec. So our molecular ion peak in this case is going to be at 79. Notice also that this molecule has 1 nitrogen, and we get an odd molecular weight. So the molecular weight is odd because we have a nitrogen atom present. The molecular weight for this one is even because we don't have a nitrogen. So let's propose a molecular formula for some of these compounds. Let's learn how to determine our molecular formula in GCMS. Okay, so let's do a couple of these. So remember that our molecular ion peak, our M+1 peak, is 1.1% as high as the molecular ion peak. So we can use that to determine the number of carbon atoms in a molecule. So how do we do that? So what we do is we take the molecular ion peak, or the relative height of the molecular ion peak, and we divide that by, the relative height of the M+1 peak, and we divide that by the relative height of the molecular ion peak, and we multiply that times 100 to give us the height, the relative height of the M+1 peak to the molecular ion peak. So let me kind of back up here. So let's say I had a spectrum. And I have relative abundance on the y-axis, and I have mass to charge ratio on the x-axis. And so I have a peak at let me see. I have a peak at 86, representing our molecular ion peak. Okay, that is 20.9% as high as the base peak. And my base peak is at 43. Okay, and that's going to be 100%. Well, my molecular ion peak is only 20% as tall as the base peak, so it has a relative abundance of 20.9. So at 43, I have the tallest peak in the spectrum. Then at 86, I have one that is 20.9% as tall as this one. So this one's going to be 100%. This is my base peak here. This is my molecular ion peak, or my M+ peak, and it is at 86. So at 87, I have this little bitty peak, and that is my M+1 peak. My M+1 peak in this case is 1.2% as high as what? As the base peak. So at 87, I have my M+1 peak that's 1.2% as high as the base peak. And then I have some other peaks here. I'm not going to worry about those. So I'm really concerned about the base peak, which is going to be 100, my molecular ion peak, which in this case is 20.9% as tall as the base peak, and my M+1 peak, which is 1.2% as tall as the base peak. Remember that my base peak is going to be 1.1% as tall as my molecular ion peak for every carbon that I have. What does that mean? It means that I need the height of the M+1 peak relative to the M+ peak, not the base peak. But I have the height of the M+1 peak relative to the base peak. So what do? I take that 1.2 and I divide it by the height of the base peak, the height of the molecular ion peak relative to the base peak, which is 20.9. So I take the relative heights of the M+ and the M+1 peak and divide the M+1 peak by the M+ peak and multiply that times 100. So that gives me 5.7%. Okay? It gives me 5.7%. That means my molecular ion peak, my M+1 peak, is 5.7% as tall as my molecular ion peak. Okay, but that doesn't tell me exactly how many carbons I have in the molecule. To get the number of carbons, I need to divide that by 1.1, and that comes out to 5.2. Well, I can't have a fractional number of carbons in my molecule, so I have to say that's about 5. So I'm going to round that to about 5 carbons. So if I were looking for my molecular formula, that means this molecular formula is C5. And I've been given the molecular weight. So my molecular weight is 86. Okay, so what is the weight of 5 carbons? So I can say C5 is equal to 12 for carbon times 5, which is 60. Okay, so 86 minus 60, okay, is equal to 26. Well, I can't have C5H26 because that's too many hydrogens. So what do I have? I have to have an oxygen somewhere. I have to have an oxygen in this molecule. So what does oxygen weigh? Oxygen weighs 16, okay? So 26 minus 16 is 10. So that means if I have an oxygen, then my molecular formula is going to be C5H10. Now, how did I know I have oxygen instead of nitrogen? Well, I don't really have enough AMUs left over to have too many things. I can't have like 2 nitrogens, and this is an even molecular weight. So I know I have to have either 2 nitrogens or I have to have no nitrogens. And the most common things to have in our molecular formula are going to be carbon, hydrogen, nitrogen, oxygen, or something like chlorine. What's chlorine weigh? Chlorine weighs 35, so I couldn't have that. So the halogens are pretty heavy in general, so I couldn't have a halogen here really. So the most reasonable thing would be for me to have an oxygen. So this is my molecular formula. Okay, so let's look at how to calculate the molecular formula for some of these other examples. Okay, so let's do, let me see, it's 15.21. Let's do A. Okay, so here I have, let me kind of sketch a spectrum up here. I have relative abundance versus mass to charge ratio, okay? And here I have my molecular ion peak at 72. So I have my molecular ion peak at 72. That's 38.3% of the height of the base peak. So I've got a base peak somewhere else, and I'm not told where that base peak is, but it has to be lower than the molecular ion peak, right? So my base peak is going to be 100%, okay? And my molecular ion peak is at 72. It's 38.3%, okay? And then I have an M+1 peak at 73, okay? That's going to be 1.7% as high as the base peak, not the molecular ion peak. So how do I find my molecular formula? Well, what I do is divide 1.7 divided by 38.3 times 100, and that's going to give me 4.4. Okay, and then to find the number, that gives me the height of the M+1 peak relative to the molecular ion peak. So then to find the number of carbon atoms, I divide that by 1.1, because I have 1.1% for every carbon atom. Okay, and so that's going to give me 4. So my molecular formula is C4 something. Okay, so 4 times 12 is equal to 48. Okay, so well, my molecular weight is what? It's 72. So 72 minus 48 is equal to 24. So I could have a nitrogen, but I couldn't have 2 nitrogens, because 2 nitrogens would be 14 times 2, which is 28. And this is even, so I can't have 1 nitrogen. So I have to have basically an oxygen here. So oxygen weighs 16, so 24 minus 16 is equal to 8. So my molecular formula is C4H8O. Alright, so let's do one more of these, and I'll let you do the rest of those on your own for homework. So we have relative abundance versus mass to charge ratio. Okay, so let's do C. So C says I have a molecular ion peak at 54, okay, and then I have an M+1 peak at 55, and the molecular ion peak is 100%. So that's my base peak. And my M+1 peak is 4.6%. Okay, so this one's 100. This is 4.6. So this is 4.6% as tall as this one. So we could just say 4.6 divided by 100 so we don't get confused, times 100 is equal to 4.6%, obviously. And then we divide that by 1.1 to get our number of carbons. And so that's equal to 4.15. Okay, so that's equal to about 4 carbons. So our molecular formula is going to be C for something. So what's our molecular weight? Molecular weight is 54. So 4 times 12, because we got 4 carbons, is equal to 48. So 54 is our molecular weight, minus 48 is equal to 6. So our formula is C4H6. Okay.